Good morning, all. We'll wait for another 2-3 minutes. Okay. So till now we are in module 3, and we are studying about the shear force and bediment in beams. Okay. So these are the internal forces that are set up in the beam due to the result of loading which are applied on the beam. Okay, loading may be anything. That is, it may be UDL, UVL, concentrated load, couple, like that. We come across different types of loading on the beams. Okay, and also we have different types of beams also. What we come across is a cantilever beam, a simply supported beam, or maybe a beam with overhang. Okay, these are some of the beams what we have considered for studying the bending moment and shear forces in the beams. Okay, so these are the internal forces, like reactions and applied forces are external forces. There are forces within the beam body. Okay, these are bending moment and shear force what we have studied here. Okay, now these bending moment and shear forces, they are also cause stresses in the beams. Okay, so we'll look into these stresses in this module. Now we'll move to this fourth module, which is about the bending and shear stresses in the beams. Okay, and another part of this module is torsion in circular shaft. Okay, we'll come to that torsion part later, but right now we'll look into the bending stresses and the shear stresses in the beams. Okay, now the direct stresses what are set up in the any member or element, we have studied them in module 1. Okay, so there what we have studied is actually the uh, direct stresses, that is when you apply axial load, what are the stresses which are there in the beams. So right, and the direct stresses what you have seen was you used to obtain them as a load per unit area, P by A. Okay, so these were the direct stresses. Like these, whenever a beam is subjected to bending, or I can say bending movement, okay, there are stresses which are set up in the beams. Okay, also we have shearing stresses which are set up due to the result of shear force that the beam experiences. Okay, so these are the two stresses what we see in case of beams: bending stress and the shearing stresses. Okay, bending stress are due to bending of the beams. Okay, the transverse bending of the beam that will result in bending stresses. Shearing force within the beam, they cause shear stresses to develop in the beam. Okay, we'll see how these stresses are actually developed. Okay, so this is what that is about: bending and shear stresses in the beams, right? Now we'll see a case of pure bending here. So what is actually this pure bending? Now let us take this particular beam. I've shown a simply supported beam over here. Okay, and it is supporting two loads, two concentrated loads of magnitude W. Okay, and the position is at every one third point of the span. Okay, so you can see here the first load is at a distance of L by 3. Okay, and the second load again, which is applied at point C, is at a distance of L by 3. Okay, or 2L by 3 from the end A. So this load, what is applied on the beam, the two concentrated loads, they are applied at every one third span. Okay, the L is the span of the beam at every one third span. Okay, now what will be the shear force in such case? If you calculate the reactions here, you'll come across W. Reaction at A will be W, whereas the reaction at B will also be, this point has become D. Okay, so this is VD, the reaction at the support D. So this is VA. Okay, so reactions at the two supports, they are equal to W here. If you calculate applying the conditions of equilibrium, you'll note that the two reactions are equal in magnitude. Okay, W and W. Okay, even by symmetry, by looking at the beam, you can conclude that since the loading applied is symmetric. Okay, symmetric means it should be symmetric in every sense. The magnitudes of the loads should also be same, and the positions should also be symmetric. Okay, so in such cases the reactions what we get, they will be half of the total load. Each support will be sharing half of the total load over here in such cases. Okay, so it will come out to be W and W. Now what will happen to the shear force? If I try calculating the shear force at these points, that is at A, B, C and D, let us see what it comes out. Now starting with A, from 0, when I cross this support A, okay, the shear force, what happens to the shear force here? It will increase to VA. Okay, the value will change to VA over here. Okay, so that is what VA, the VA is here W. So this is W. Okay, it will increase to W. Okay, directly I'm plotting it. I hope you are now good enough with this calculation of shear force and bending moment. Okay, so if I look at that section, and if you try this one calculation, okay, so the section first what I have taken is over here. This is my cross section in the beam what I am considering, right? So now when I take the section at A, okay, so when I cross this point A, the shear force will increase to W. So left side upward force, I'll be taking that to be positive. Now from point A to B, the shear force will remain constant. When I move anywhere this section between A and B, okay, anywhere you take this section between A and B, what you'll come across is the sum of forces to the left side of the section will remain VA only, which is equal to W. so it will remain constant. Now when I come to point B and when I cross this concentrated load, okay, now what happens here? What are the forces to the left of the section? It is VA and this downward force W. Okay, so VA is W and it is acting in a upward direction. Left side upward force is positive, so VA will be taken to be positive, whereas this force, concentrated load, which is applied at B, it is in downward direction, so it will be considered negative. So if you calculate this shear force at B, okay, and left of B, to the left of B, it is just VA, which is equal to W. Okay, to the right of B, just wait. Okay, we'll resume that one. So to the right of B, okay, if you follow your procedure, what we had done in previous module, so right side of B, when you, I mean, when you cross this concentrated load, it will be equal to VA minus that applied concentrated load W. So that comes out to be 0 because VA is also equal to W in our case. Okay, so here the shear force is 0. Now again, if I take my section between B and C, anywhere between B and C, if you move your section, okay, up to point C, you'll notice that the shear force is 0 only. It will remain 0 because we are taking sum of all the forces to the left of section. Okay, that is how you calculate the shear force. Either you take algebraic sum of all the forces to the left side of section or to the right of section. Any one side you have to consider. So if I consider to the left of the section, I have VA upwards plus VA or plus W and this downward force concentrated load W. So plus W minus W, it will remain 0 only. Okay. Now if we move ahead of C, okay, that is when we cross this concentrated load at C, there what happens to the shear force now? So if we calculate that shear force at C, at point C, so if you take left of C, okay, so it will be equal to VA minus W itself. So this is nothing but W minus W, which comes out to be 0. That's what I told. Between B and C also it will remain 0. To the right of C. So what happens? What are the forces which are coming on the left side of my section now? One is this reaction VA, which is equal to W. Okay, left side upward force, I'll take it to be positive W. Then next is this downward force at B, which is negative, left side downward force negative minus W. Then at C we have one more concentrate load applied over here, which is in downward direction, so again minus W. So this gives me the total shear force at C, to the right side of C, as minus W over here. Okay, so this is also W up to this point. Now here from 0 it is coming out to be minus W. Okay, this is what you get. Now after this, again between C and D, what you have between C and D, the shear force will remain constant, okay, with a value equal to minus W. Okay, the value is same and it will remain unchanged till you cross this point D. Till you take your section to the right of D, this will remain as minus W itself. Okay, up to this point. Once you move ahead of this point D, when you cross this reaction at D, it comes to 0. Okay, that is plus W minus W minus W, and this is also upwards plus W. Okay, so that will reduce to 0. Okay, we should calculate that one. So this is how the shear force variation is taking place in this beam, in this particular beam. Okay, is that clear for you? I just calculated the shear force for one of the cases, okay, where a concentrated loads have been applied at every 1/3 span. Now there is a purpose for this. What I'm going to show over here, it will be clear. So what I have is, this is my shape force diagram. Now if I go for calculation of bending moment diagram, okay, by taking section at these points. So at A, bending moment will be 0. When you come to point B, what will happen to the bending moment value? It will be this VA into L by 3, or it will be W L upon 3 over here. Okay, left side clockwise movement, it will be positive. Okay, left side clockwise movement, so positive. And once I come to next point, what is my next point here? It is C. Okay, I'll calculate the bending moment at point C. Now what is the value of bending moment here? W. Okay, I just calculate here. So that will come out to be W, that is VA into 2L by 3. L by 3 plus L by 3. VA into 2L by 3 minus W into L by 3. That is how you get the bending moment at point C. You can verify this calculation, don't worry about that. Just concentrate on what I am telling. So bending moment at A, it will be 0. That is one thing. Bending moment at B, it will be VA into L by 3. This is W in L by 3 over here. Okay, plus because it is left side clockwise movement. Okay, don't forget these sign conventions. And then bending moment, what we want next point is at C. Okay, at point C over here. So it will be VA into 2L by 3, because what is the distance of VA from my point C? VA into L by 3 plus L by 3. So VA into 2L by 3. Left side clockwise, I have taken that positive. Then because of this concentrated load W at B, what is the moment at C? Due to this W, the moment, what moment it will have at C is W into L by 3. Now this is left side but anti-clockwise movement. So minus W into L by 3 over here. So what it comes out to W L by 3 minus W L by 3. So this will give us as W L by 3 over here. Okay. Now, if you take point D, okay, there the bending moment will be 0. Okay, and support. So here it will come to 0 again. Even your calculation will give you 0 value over there. So this is what the bending moment diagram is. This is how the variation in bending moment is. Now what is happening? Just look at this two diagrams. What's the shear force diagram and the bending moment diagram. Now we have calculated and we have drawn these shear force and bending moment diagram over here. Okay. Now you just look at these two diagrams. What is happening over here is, in this portion over here, okay, between B and C, what I have taken here, in this portion, the shear force is 0. Okay, so there's no shear force. The shear force value is remaining 0 between B and C. Okay, so such a case where you don't come across any shear force, okay, and bending moment is existing over there. So such a case where shear force is 0, we call it as a pure bending, a case of pure bending. This is what the pure bending means. Okay, so the portion BC of this beam is subjected to pure bending here. Okay, what is pure bending? The bending moment where shear force is 0. Okay, that portion of the beam we call it as pure bending. Okay, now this is what the pure bending means. Okay, so this is an example of this beam. With the example of this beam, we have looked into what is that pure bending is. Okay, I hope that is clear. What is pure bending? In simple words, I can say bending where shear force is 0. Okay, bending at portion of a beam where shear force is 0. That is a pure bending case. That is what we call it as pure bending. Okay, now we have seen with this example of this beam what is the pure bending, or this part of the beam is subjected to pure bending over here. This portion BC of the beam is subjected to pure bending. Fine. So that is the one thing what you need to understand, how the pure bending exists in a beam and what is that pure bending. Okay. So there may be other beams also with other type of loading where you come across pure bending. Okay. One more example is a beam subjected to end couples. Okay. So something like this. Okay. So in such case also you may have pure bending case. Okay. So that is also a pure bending over here. Now, once we have understood this pure bending, okay, pure bending theory, that is what the pure bending theory is meant. Okay. Now let us move ahead. So now if I look at this beam, how it is behaving. Now I was talking you about the sagging and hogging moment in the previous module. Okay. So here it is the sagging moment. The beam is bent in this way. Curvature is downwards. Okay. Whereas in case of hogging moment, the curvature is upwards. It is hogging actually, not hagging, hogging. Okay. So these are the sagging and hogging nature of the beam. Okay. Here the beam is sagging. Okay, you may see the sag in case of a ropes tied, so this is something like that. Okay, so sagging moment or sagging nature of beam and hogging nature of beam. Okay, now what is actually happening in this beam under such a situation is the top portion. Okay, there is something called neutral axis. I'll tell you later, we'll understand that. But what is happening here is the top portion of the beam is getting compressed. Okay, and the bottom portion is getting elongated. Okay, so here compressive stresses are set up over here, whereas in the bottom portion tensile stresses are set up here. Okay, where there is an elongation at that portion of the beam, the beam is experiencing tensile stresses, whereas in this top portion where the beam is being compressed, it is experiencing compressive stresses. So this is how bending induces stresses in a beam. Okay, this is in case of sagging moment. If you take a beam which is subjected to hogging moment or hogging nature, so there what you find is the top portion of beam will be elongated, whereas the bottom portion of the beam is being compressed. Okay, so due to this, in the top region, the tensile stresses will be set up, whereas in the bottom region, the compressive stresses are being set up over here. Okay, so that is how the bending stresses come in picture in the beam. Okay, so these are the bending stresses what we have in the beam. So bending will induce both type of stresses, tensile as well as compressive, in the same member. Okay, so in case of sagging, what you find is the top portion of the beam over here like this, it will be experiencing compressive stresses, whereas bottom portion will be experiencing tensile stresses. Okay, so in case of hogging movement, the top portion will be experiencing tensile stresses, whereas bottom portion will be experiencing compressive stresses. Now we are going to study such stresses in this particular module. These are bending stresses. Okay, shear stresses we'll see later, but right now these are what the bending stresses are. Okay, we are going to come across these particular stress in the beams. Okay, so look, you can look at the bent nature of the beam. This is how the beam is bent. Okay, just excuse me. Hello, sir. Right. So what you have is this is a normal beam. What you find, okay? Before I apply the load, this is how a beam you will be having in its position. Okay. Once you apply the load, okay, it may be movements like this at the ends, okay, or there may be a UDL present on it, or there may be a concentrated load. Okay, any kind of loading may be applied on it. So due to the application of load, it will experience bending. It may experience sagging bending or hogging bending, any type of bending. But thing is, it will bend into a curvature. Okay, this is the radius of curvature. Okay, and it will bend into a curved form over here. Okay, so that is what we have. And you see here, this is the stresses what is shown here. Okay, we'll study this, and right now you don't worry about this particular part. Okay, this diagram, what I want to make it clear is what are the planes in the beams. This is the transverse plane what you see here. Okay, if I take a cross section perpendicular to the axis of the beam, that is a transverse plane over here. Okay, this is our plane which is perpendicular to our axis of the beam. So that is the plane on which you'll find the bending stresses are applied. Okay, the bending stresses on which plane they are applied is on a plane which is perpendicular to the axis of your beam. This is the axis of the beam. If this is x-axis or the longitudinal axis of the beam, the bending stresses will be acting on a plane which is perpendicular to this beam or on the cross section of the beam. In simple, I can say on the cross section of this beam, on this cross section of the beam over here. So this particular cross section, it will be subjected to those bending stresses over here. Okay, so here you can see the bending stresses, what sigma x is there, that is the bending stress. We are taking up this particular stresses. So in case of sagging bending or a sagging nature of beam, compression will be there on the top, tensile stresses will be there on the bottom. Okay, so this particular diagram is showing you that those stresses how they will be. Now before we get into any derivation or further, we have some assumptions what are taken up in these study of bending stresses and the shear stresses. So what are these assumptions? The first assumption is the beam is initially straight. Okay, that is, the beam will be straight initially before you apply the load. It is straight. It is not in any curved form. It is not bent. It is perfectly straight. That is what this assumption means. The beam is something like that, not a bent form. It doesn't have any bent form like this. Okay, so it is straight. You can see in this diagram also, beam is straight initially means it is perfectly straight. It is not having any curvature or any bent shape over there. It is not a curved beam, it is a straight beam. So it is perfectly straight initially. That is what the first assumption is. Okay, now second assumption is plane cross section normal to the axis of the beam remain plane even after bending. The plane cross section, okay, normal to the axis of the beam remain plane even after bending. Now what it means is, if I take a cross section, okay, like this within the beam, okay, the cross section of the beam which is plane before application of load will remain plane even after application of load. Even after bending, it will remain plane. Okay, it will not bend like this. It will not get distorted. Okay, I hope you can see this particular figure over here. So here, what you have is the plane has been bent over here. Okay, it has undergone distortion. It is bent here. So this thing will not happen in our case. Okay, this will not happen. That is what it means. So the sections will not get distorted. The plane section, say this Q and S, this is one plane section. So even after application of load, it will remain plane only. It may get rotated here, okay, but it will remain as a plane element. Okay, so this is the plane before the application of the load. Okay, so once you apply the load, when the beam is bent, it may become like this. It may get rotated, but it will remain straight. It will not be distorted, or it will not be in the curved form. It will not take this form. Okay, that is what it means. Plane sections in the beam remain plane even after bending, even after application of bending moment. Okay, so that is the meaning of this particular assumption. Okay, so that is one second assumption. What we have, plane section, now the plane cross section normal to the axis of the beam remain plane even after bending. Okay, the curvature of the beam is small and radius of curvature of the beam is large as compared to the depth of the beam. Okay, you measure the curvature by this r, okay, by its radius. So this curvature of the beam is very small. You'll not even notice the bending of actual beams. If you look at any beam in practical, you'll not notice the curvature, you cannot see it. Okay, so this curvature of the beam is small, whereas this radius of curvature is very large as compared to the depth of the beam. If you compare this r and the depth of the beam, say if I say d is the depth of the beam. Okay, so if this is the depth of the beam, say d. Okay, so this r is very large as compared to d. Okay, that is the uh, assumption what we have taken up over here. The curvature is very small and radius of curvature is very large as compared to the depth of the beam. Okay, so that is the third assumption what is there. Now the fourth assumption is modulus of elasticity of the beam is same in tension and compression. Okay, whether you measure the modulus of elasticity by taking the tension test or the compression test. Once you come to the lab and all, you'll understand how we calculate modulus of elasticity. Okay, we actually have the lab of testing the basic materials. There you'll see how to calculate the modulus of elasticity. Even in the first module, you must have come across some problems in which test results are given to you and you are asked to calculate the modulus of elasticity. So when you do the find out the modulus of elasticity, it will come out to be same in tension as well as in compression. Okay, that is the assumption, because in this particular stresses, or when you are studying the bending stresses, you will come across both tensile as well as compressive stresses. So what this assumption is telling you is, in these two cases the modulus of elasticity will remain same. Okay, so we are not considering any difference in modulus of elasticity in tension or in compression. It is taken to be same in both cases. So that is another assumption what we have here. And lastly, the material of the beam is homogeneous, isotropic, and obeys Hooke's law. Okay, homogeneous means it is same throughout the length of the beam. The material is homogeneous, it is of same material properties. Okay, same material is used. If the beam is of concrete, for the entire length of the beam it is of concrete. If it is of steel, for the entire length it is of steel. That is the homogeneity of the material. It is not changing in between, it is not composite or heterogeneous material. The material is not changing in between. So the material of the beam is homogeneous, that is one thing. Then what you have is, it is isotropic. What it means, isotropic means, what is this isotropy? You must have studied in physics. So the properties of the material are same in all direction. Okay, whether you take x direction, y direction, or z direction, in any direction, modulus of elasticity is same. Okay, Poisson's ratio is same. Any property you consider for that material, it will remain same in all the direction. It is not that if I bend the beam in some other direction, it will give me some different results. No, the properties are different. No, it is not like that. The properties, like material properties, modulus of elasticity, Young's modulus, or the bulk modulus, or modulus of rigidity, any property you take, they will remain same in all direction. Okay, so that is what isotropic means. So homogeneous and isotropic. The material of the beam is homogeneous and isotropic. And one more is obeys Hooke's law. Obeys Hooke's law means stress and strain are directly proportional. Okay, within the elastic limit, stresses and strains are directly proportional. and whatever bending we are taking, it will be within the elastic limit. We are not exceeding the elastic limit. So these are five assumptions, five basic assumptions. If you take up the books, you may come across some more assumptions, but these are the major five assumptions what every book will consider, or which are required in this particular module when we take up the derivation or any other thing. So what are the first assumption is beam is initially straight, perfectly straight before the loading. The next one is the plane cross section normal to the axis of the beam remain plane even after bending. Cross sections which are plane before bending will also remain plane even after bending. There will not be any distortion like this. Okay, that is the second assumption. Third assumption is curvature of the beam is small. Okay, this curve, what you have seen here, it is very small. Or radius of curvature is very large when compared to the depth of the beam. Okay, that is the third assumption. And the fourth assumption what we have is modulus of elasticity is same in tension and compression. Modulus of elasticity or Young's modulus is same in tension and compression. And the material of the beam, the material by which this beam is made up, it is homogeneous, isotropic, and obeys Hooke's law. These three things. Okay, so that is the assumption. These are five assumptions. Okay, pure bending. What is meant by pure bending? We are seeing a case wherein shear force is zero. A case of bending where you have zero shear force. That is the pure bending. That is what it means by pure bending. Okay, so that is what I wanted to start with now. So we have the derivation of bending equation. We'll take up that in the next class. Okay, but before that, these things should be clear for you. What we have seen, assumptions, what is pure bending, and the assumptions here. Okay, other than that, we have come across the bending stresses. Okay, Tirthraj, are you there? Tirthraj,
Yes, sir.
any doubts?
No, sir, by mistake I was dying.
Okay, so this is the bending nature. I hope this sagging and hogging movement bending are clear to you. Okay, sagging, hogging, they are clear in your mind. Only when you understand what is sagging and what is hogging, you'll be able to what you can say. You will be able to see what nature of stresses will be there. Okay, at what location in the beam, what nature of stresses will be coming over there. Okay, yes. Any doubt in this? What I was talking about? If you have any doubts in this particular part, because this entire model, these things should be this will form the basis for the this one. Okay, please give your attendance. Tomorrow class we'll take up that derivation part. We'll finish with this much today. If you have any doubts, you can ask, or else we'll finish. You can exit the meeting if you have given the attendance.